The problem of robust matrix completion, RMC, is addressed, where a partially observed low-rank matrix is corrupted by sparse noise. A non-convex method is proposed, alternating between a projected gradient step for the low-rank part and a thresholding step for the sparse noise part. This method achieves linear convergence for a general class of thresholding functions, including soft thresholding and SCAD, as established through leave one out analysis. This result improves the sampling complexity of existing results for low-rank matrix completion. Three assumptions are introduced. 1. The ground truth matrix L-star operator is mu incoherent. 2. Each entry is independently observed with probability p. And 3. Each observed entry is independently corrupted by an outlier with probability alpha. These assumptions are standard in the matrix completion literature and serve as separation conditions on L-star operator, S-star operator. The non-convex RMC algorithm combines the SVP algorithm for low-rank matrix completion with a thresholding function to handle sparse outliers. A general class of thresholding functions is considered, satisfying three properties. 1. 0 for inputs less than or equal to a parameter lambda. 2. Lipschitz continuous. And 3. Bounded difference with the identity function. Algorithm 1 is proposed, using a general thresholding function satisfying these properties, with a theoretical guarantee applicable to any such function. Phase transition tests suggest that soft thresholding and SCAD functions work desirably, as they satisfy the three properties. The non-convex method is applied to the RRMC algorithm, combining SVP with hard thresholding for outliers. Limitations of the leave one out analysis in 11 and difficulties in extending it to RRMC are discussed. The paper presents a novel approach to robust matrix completion, focusing on the recovery of low-rank matrices from corrupted and incomplete data. The authors introduce two algorithms, RMC-SOFT and RMC-SCAD, which leverage non-convex optimization techniques to efficiently solve the problem. These methods are compared with existing approaches, such as RPCAGD and RRMC, through extensive numerical experiments. The authors first provide an empirical phase transition comparison for RMC-SOFT and RMC-SCAD, demonstrating their effectiveness in various scenarios. They then outline the key steps of their proposed algorithm, which involves an initialization step followed by a series of iterations that progressively refine the estimate of the low-rank matrix. The algorithm utilizes a thresholding function to eliminate outliers and noise from the data. The paper also includes a detailed theoretical analysis of the algorithm's performance, providing conditions under which the proposed method can successfully recover the underlying low-rank matrix. Specifically, the authors establish that if certain assumptions are met, including a sufficient number of samples and a suitable choice of parameters, the algorithm will converge to the correct solution with high probability. Numerical experiments are conducted to compare the performance of RMC-SOFT, RMC-SCAD, RPCAGD, and RRMC across different problem settings. These tests demonstrate that the proposed algorithms outperform existing methods in terms of both accuracy and computational efficiency, particularly when dealing with high-dimensional data and large outlier probabilities. Overall, this paper contributes significantly to the field of robust matrix completion by introducing novel algorithms and providing a comprehensive analysis of their performance. The proposed methods offer promising solutions for real-world applications involving large-scale, noisy, and incomplete datasets. Here is the combined summary of pages 912. The paper establishes Theorem 2, which provides bounds for certain inequalities with high probability, under the assumptions of Theorem 1. These inequalities include bounds for the maximum of at 1, I and dt, I, m for various values of I and m. To prove Theorem 1, the paper considers two cases. T equals 0 and t is greater than or equal to 1 . For t equals 0 it is shown that L0L is bounded by micro Rn sigma 1 and hence sup S0 subset equal omega S and p omega S0s is bounded by C thresh micro Rn sigma 1 . For t is greater than or equal to 1, the paper applies lemma 1 to obtain a bound for LTL involving increment t ft f and sigma t . The key differences between the proofs in this paper and those in 11 are discussed, including the use of lemma 4 to bound h omega L and the application of Bernstein's inequality to vectors instead of scalars. The paper then establishes the induction hypotheses for t equals 1 and t greater than 1 . For t equals 1 it is shown that E0 I is bounded by gamma 2c01 kappa 2 micro r sigma r with high probability, where E0 I is decomposed into two terms, E0 I1 and E0 I2 . Finally, the paper provides the eigendecomposition of L and expresses increment 1 Im as the sum of four terms, T1 T2 T3 and T4 . Bounds for T1 and T2 are obtained using lemmas 7 and 4, respectively. The analysis begins by bounding the matrix increment 1, infinity, a crucial component in matrix perturbation analysis. The authors decompose the matrix into two parts, leveraging the property of V1, M to bound one part. They introduce a new variable, Vk, to bound the norm of the matrix, and apply lemma 10 to obtain a bound involving the norms of L star operator and V1, M. The authors then bound the matrix norm of EdMe0, IV1, MG1, I, M by splitting it into two parts and bounding each separately. The first part is bounded using the property of the matrix norm and equation, 4, while the second part is bounded using equation, 5, and the property of the matrix norm. Combining these bounds, they obtain a bound for the matrix norm of EdMe0, IV1, MG1, I, M. The bounds for T1 to T4 are combined to obtain a bound for the matrix norm of increment 1, infinity, involving the norms of L star operator, V1, M, and D1, infinity, as well as parameters C0, C10, C4, gamma, and kappa. The matrix norm of D1, infinity is bounded by splitting it into two parts and bounding each separately, using Weyl inequality and the bound of EO, M for the first part, and lemma 8 for the second part. In the context of quantum computing, the authors introduce a new quantum error correction code that combines classical and quantum error correction methods to protect both classical and quantum information. The code is designed to offer improved error correction capabilities, particularly against decoherence and other quantum noise. The authors analyze the code's properties and performance, comparing it to existing codes and discussing its implications for achieving fault-tolerant quantum computation. The proof of the bound for increment t plus 1, I infinity, 2, infinity is presented, which is a crucial step in establishing the convergence rate of the proposed algorithm. The bound is derived by splitting the estimation into four terms, T1, T2, T3, and T4, and then bounding each term separately. The bounds for the first three terms are obtained similarly as in the base case, resulting in a bound of 16 C0, 1, kappa micro r, gamma t plus 1. To bound T4, the case where 0 is less than or equal to I is less than or equal to n, 1 is less than or equal to m is less than or equal to n, and I does not equal m is considered. The bound for ETMET, IVT plus 1, I2 is derived, which involves bounding ETMET, I2VT plus 1, I. This is technically involved, and the proof is divided into three parts: bounding T1, T2, and T3. Bounding T1 involves applying lemma 10 to get a bound of C10, square root, n log n, p, plus square root, log n, p, lt, ml star operator infinity sign vt plus 1, m2, infinity. This bound is further simplified to C10 C0, sigma star operator r, kappa micro r, gamma t plus 1, square root, micro r, n, plus increment t plus 1, infinity 2, infinity, provided that p is greater than or equal to 576c210 gamma 2 kappa 2 micro 2 r2 log n. Bounding T2 involves expressing LT, MLT, I as the sum of four terms, and then bounding each term separately. The bound for T2 is derived as ETMH, I, omega, dt, m, IU sigma t, m, vt, m, t, vt plus 1, m2, which is further simplified to C10 C0, sigma star operator r, kappa micro r, gamma t plus 1, square root, micro r, n, plus increment t plus 1, infinity 2, infinity. The bounds for T1 and T2 are crucial in establishing the convergence rate of the proposed algorithm. The final bound for increment t plus 1, I infinity, 2, infinity is obtained by combining the bounds for the four terms, T1, T2, T3, and T4. To derive the bounds for T2a, T2b, and T2c, the authors apply lemmas 11, 10, and 9, respectively, and utilize the bounds for T2a and T2b to establish an upper bound for T2c. The authors then bound T3 by applying lemma 5, resulting in an upper bound in terms of logarithmic functions and the eigenvalues of Vt, m and Vt plus 1, m. The authors assume that P satisfies certain conditions to ensure the validity of these bounds. The paper provides technical proofs for bounding various terms in a machine learning model. On pages 21 and 22, the authors derive bounds for the terms $wide tilde, t, underscore $1 to $wide tilde, t, underscore $3, which are used to establish the convergence rate of the model. The bounds are obtained by applying various inequalities and using the properties of the model's parameters. The authors first bound the term $wide tilde, t, underscore $1 by using the inequality $wide tilde, e, underscore, m, I, v underscore, t plus 1, I, wide tilde, e, underscore, m, I, v underscore, t plus 1, m, underscore 2, lec 3 plus 2 c underscore, 10, c underscore 0, sigma underscore r caret, kappa, mu underscore r, caret, 1/2, gamma underscore t caret, 1/2, plus 3 plus 74 c underscore, 10. C underscore 0, delta underscore, t plus 1, infty, dollar. They then combine this bound with the bounds for $wide tilde, t, underscore $2 and $wide tilde, t, underscore $3 to obtain a final bound for $wide tilde, t, underscore, m, I, v underscore, t plus 1, I, v caret, underscore $2. On page 22, the authors focus on bounding the term delta underscore, t plus 1, 0, m, dollar. They use the inequality delta underscore, t plus 1, 0, m, lec 2, sigma underscore r caret, w underscore, t, m, f underscore, t plus 1, m, w underscore, t, m, f underscore, t plus 1, m, caret, underscore f dollar and then derive bounds for the terms $b underscore $1 to $b underscore $4. To bound $b underscore $1, the authors use a technique inspired by 9, where they consider an equivalent model that generates omega underscore s caret dollar. They show that p caret m omega s underscore ts underscore t caret v underscore t plus 1 m underscore f dollar can be bounded using lemma 13. They also derive a bound for u underscore t plus 1 m g underscore t plus 1 m caret t sigma underscore t plus 1 m caret 1/2 u caret sigma caret 1/2 underscore 2 infty dollar. The authors use these bounds to establish the convergence rate of the model and provide a final bound for delta underscore t plus 1 infty dollar. The results are obtained under certain assumptions on the model's parameters, such as $c underscore 0, geq 6 c underscore 10, c underscore 13 dollar. Overall, the paper provides a technical analysis of the machine learning model, deriving bounds for various terms and establishing the convergence rate of the model. The results are obtained using a range of mathematical techniques, including inequalities and probabilistic arguments. The quantum approximate optimization algorithm, QAOA, is introduced as a novel approach to minimize the expectation value of a given Hamiltonian. The algorithm utilizes variational parameters to optimize the expectation value, and its performance is analyzed in detail. A comparison with the quantum phase estimation, QPE, algorithm reveals that QAOA can achieve better performance in certain cases. The authors provide a bound on the error of the QAOA algorithm, which depends on factors such as the number of qubits, circuit depth, and variational parameters. The convergence properties of the algorithm are also analyzed, showing that it converges to the optimal solution under certain conditions. Theoretical recovery guarantees for the non-convex alternating projection method in robust matrix completion are established through leave-one-out analysis. The method's performance is ensured by the choice of parameters, including the thresholding function, which must satisfy specific conditions. The conditions involve constants C10, C0, and C13, as well as parameters p and alpha, which must fall within certain ranges to guarantee the induction hypothesis. A bound on the error of the recovered matrix is provided, depending on the problem's parameters and constants. The analysis relies on a combination of mathematical techniques, including leave-one-out analysis and the use of specific thresholding functions. The results contribute to the understanding of robust matrix completion and provide a foundation for future research. Potential future work includes accelerating the projection onto the low-rank part via Riemannian optimization and extending the analysis to robust completion of Hankel matrices and tensors. The connections between matrix completion, robust principal component analysis, and related areas are highlighted through the provided references. The paper presents a collection of lemmas and supplementary proofs that establish a theoretical framework for understanding the behavior of certain matrix functions and their properties. Lemmas 39 provide bounds on the spectral norms of various matrices, including alpha-sparse matrices, matrices with rank at most k, and matrices with small spectral norm. These lemmas are crucial in establishing the convergence of the proposed algorithm and providing bounds on the errors involved. The paper also defines several matrices, including L, F, and F, which are used to establish the convergence of the algorithm. Lemmas 6 and 7 provide bounds on the differences between F and Fg, and sigma G and G sigma, respectively. Lemmas 8 and 9 provide bounds on the differences between F and AF, and lambda G and Ga lambda, respectively. The proofs and lemmas establish a theoretical framework for understanding the behavior of matrix functions and their properties. The Davis-Cohen theorem is used to bound the difference between two matrices, G and H. The Bernstein inequality, stated in lemma 10, provides a bound on the sum of independent random matrices. Lemmas 11 and 12 introduce deterministic bounds on the norms of certain matrix functions. Lemma 13 presents a high probability bound on the norm of a matrix function, specifically the matrix H omega, XYT. This bound is established under certain conditions on the matrix X and Y. Finally, lemma 14 introduces the soft thresholding function and the SCAD function, which are used to establish three properties, p.1 p.3, essential for the analysis of matrix functions. Key equations, such as the bound on the spectral norm of a matrix H omega, Z, and the bound on the inner product of two matrix functions, are presented. The results provide a solid theoretical foundation for understanding the behavior of matrix functions and their properties, establishing bounds on the norms and inner products of these functions. The authors present a rigorous proof for lemmas 1 and 2, which are crucial in establishing the theoretical guarantees of the smoothly clipped absolute deviation, SCAD, penalty function in low-rank matrix estimation. The SCAD function, Tscad lambda, a, x, is a piecewise linear function with knots at plus or minus lambda, plus or minus 2 lambda, and plus or minus a lambda, and is shown to be Lipschitz continuous with a Lipschitz constant of a caret 1, a2, and have a bounded difference with the identity function. The proof for lemma 1 involves bounding the spectral norm of the difference between two matrices, L and L star operator, by decomposing the difference into four terms, R1, R2, R3, and R4, and bounding each term separately using various matrix norms and inequalities, including the Frobenius norm, the spectral norm, and the 2 norm. The authors rely on lemma 7, which provides a bound on the 2 norm of the difference between 2 matrices, and utilize the augmented matrices, hat-wide L and hat-wider L star operator, constructed by appending the matrices L and L star operator with 0 rows and columns, respectively. The proof for lemma 2 involves bounding the magnitude of the entries of the matrix MLT, I, where LT, I is a truncated version of the matrix L. The authors use the properties of the thresholding function T and the definition of the SCAD function to establish the desired bound. Throughout the proofs, the authors employ various lemmas and inequalities to establish the theoretical guarantees of the SCAD penalty function in low-ranked matrix estimation.